Hi, my name is Taroshi, and today I'll be explaining how the Euler method works when applying it to approximate the solution of IVP and to solve the given equation. Euler's method is a numerical technique for approximating solutions to ordinary differential equations with a given initial value. Let's start with a first-order differential equation. This equation tells us the slope of the solution curve at any point. Even if we don't know the exact solution, we can approximate it using Euler's method. We begin at a known point on the curve, say x0, y0. Next, we take a small step to the right along the x-axis to estimate the y value at a new point, x1. Euler's method helps us approximate this new y value at x1 by using the slope of the tangent line at the point x0, y0. The slope between these 2 points is simply the rise over run. But from the differential equation, we already know that dy dx equals to f bracket x comma y bracket. By setting these two slopes equal, we get this. If we let the step size h equals to x1 minus x0, we can rearrange this equation. This formula let us approximate y1 using the slope at x0, y0. If we want to continue this process over multiple steps, we repeat it by treating the current point as the new starting point for the next step. This gives us the general formula for Euler's method, allowing us to approximate the solution step by step along the curve. Let's walk through how I solved the initial value problem using Euler's method in Excel to approximate the value of y of 1 and then compare it with the exact solution. First, I set the step size h to 0.1. Then, I entered the initial values. At n equal to 0, I set x equal to 0 and y equals to 1. For the x column, I wanted x to increase by the step size h at every step. So in the cell below the initial x value, I typed equal, selected the cell above, then added plus, and clicked the cell where I stored h. To make sure the reference to h stayed fixed when I filled the column, I used absolute referencing by adding dollar signs. Then, I dragged the formula down the x column, continuing until x reached 1 since I was solving for y of 1. Next, I added the dy dx column to calculate the slope at each step using the differential equation. In this case, the slope is defined as dy dx x squared plus 1 over y. So in this column, I typed the formula using x and y values from the same row. Then I dragged the formula down to fill the rest of the column. Next, I filled in the y column using Euler's method. In the next y cell, type equal previous y value plus step size times the slope expression, which is the previous dy dx cell value. Once that was done, I dragged the formula down the y column. The final value in the y column gave me the approximate value of y of 1, which is 1.911375. To compare my Euler's method results, I also solved the differential equation using general solution. This is a separable differential equation. The exact solution from the general formula is 1.9149. So the absolute error is about 0.003 at 3 dB. To make the approximation more accurate, I reduced the step size to 0.05. Since the steps are smaller, I needed twice as many steps to reach x equal to 1, but the final y value was much more closer to the actual solution. With h equal to 0.05, the Euler method gave me 1.912934, so the absolute error is 0.002. The blue curve represents the exact solution 1.9149. The green point with step size h equals to 0.05 gives an approximation of 1.9129, which is very close to the exact value. In comparison, the red point using a larger step size h equals to 0.1 gives 1.911375, which has a slightly larger error. This visual comparison highlights that smaller step sizes lead to more accurate results, reducing the approximation error significantly.